Hello everyone, and welcome to an introduction to linear regression. In this lecture, we're going to give a light theoretical background and history behind the idea of linear regression before we actually tackle the concept with Python and the scikit-learn library. If you want a deeper mathematical understanding of linear regression, you can go ahead and check out chapters 2 and 3 of an Introduction to Statistical Learning. Let's discuss the history behind linear regression. This entire idea all started back in the 1800s with a man named Francis Galton. Galton was studying the relationship between parents and their children, and in particular, he investigated the relationship between the heights of fathers and the heights of their sons. What he discovered was that a man's son tended to be roughly as tall as his father. However, Galton's breakthrough was that the son's height tended to be closer to the overall average height of all people. Let's go ahead and take an example of this. Shaquille O'Neal, who's a famous NBA player, is very tall. He's 7 foot 1 inch, or 2.2 meters tall. If Shaq, as he's known, has a son, chances are he'll be pretty tall too. However, Shaq is such an anomaly in height that there's also a very good chance that his son is not going to be as tall as Shaq. And it turns out this is the case. Shaquille O'Neal's son is pretty tall. He's 6 foot 7 inches, but he's not nearly as tall as his dad, who was 7 foot 1. Galton calls this phenomenon regression, as in a father's son's height tends to regress or drift towards the mean or average height of everyone else. Let's go ahead and begin to plot out this sort of example. Let's calculate a regression with only 2 data points, which is the simplest possible example. Here we have 2 data points at x equals 2 and y equals 4 is one data point, and then x equals 5 and y equals 10 is another data point. These 2 little black dots. All we're trying to do when we calculate our regression line is draw a line that's as close to every dot as possible. For classic linear regression, or the least squares method, you only measure the closeness in the up and down direction. Here we have a perfectly fitted line because we only had 2 points. Now, wouldn't it be great if we could apply this same concept to a graph with more than just 2 data points? By doing this, we could take multiple men and their sons' heights and do things like tell a man how tall we expect his son to be before he even has a son. And this is the idea behind supervised learning. We're going to have a bunch of labeled data points, create a model, in this case a linear regression, and try to take unlabeled data, such as a father's height, and spit back out labeled data, our prediction of the son's height. Our goal with linear regression is to minimize the vertical distance between all the data points and our line. So in determining the best line, we are attempting to minimize the distance between all the points and their distance to our line. There are lots of actually different ways to minimize this, the sum of squared errors, sum of absolute errors, etc. But all of these methods have a general goal of minimizing the distance between your line and the rest of the data points. For example, one of these most popular methods that we just described is the least squares method. Here we have a couple of blue data points along an x and y axes, and we want to fit a linear regression line. And the question is, how do we decide which line is the best fitting one? We can go ahead and use the least squares method, which we discussed earlier. This method is fitted by minimizing the sum of the squares of the residuals. The residuals for an observation is the difference between the observation, the y value, and the fitted line. In this image, the residuals are marked by the red line, the difference between the true data point in blue and your fitted model line, the black diagonal line. Alright. In the next lecture, we're going to use scikit-learn and Python to create a linear regression model. Then you'll have your own portfolio project exercise, and afterwards, we'll go over the solutions to that project. Thanks everyone, and I'll see you in the next lecture.